Hey Peter, thanks for the follow. Hey everyone, this is Nick from Engineering Today. Thank you for joining me today. And today we've got something especially fun planned. We're going to be taking a first look at the processor from that computer architecture book, Computer Organization and Design, the RISC-V edition. So thanks for joining me. Let's get started. All right, so here we are. We've made it all the way to Chapter 4. We went over what the basics of a computer is in Chapter 1 and 2, and a little bit about how to collect performance metrics on computers. Then in Chapter 3, we looked a little bit at computer arithmetic and how does a computer actually do math. Math is really the central part of a computer. And so now we're moving on, really past these things, and this is the first time we're going to see, well, what's going on under the hood, what's happening, what does a processor actually do. So, without further ado, we can go ahead and start. Let's zoom in a little bit. Okay, it's drawing today. Sometimes it doesn't draw. It's good. We've got a drawing day today. So let's get started. Pull up the highlighter. Whoops. We'll do a nice yellow today. Processor. Okay, so this chapter is going to describe how processors exploit implicit parallelism. So we already know that we can break data up, or we can break things up into different chunks and do them concurrently, but we'll see that there's other types of parallelism that we can exploit as well. Things like thread level parallelism, instruction level parallelism, and data level parallelism. We can really break these down into a lot of different categories. So it contains the explanation of the principles and techniques used in implementing a processor. So we'll see that these same designs are used not only in Intel processors, but in ARM processors, and every architecture we can think of, besides maybe a couple fringe ones on the outside. A lot of these core components are the same. So specifically, we're going to be talking about how to design a processor for something like the RISC-V instruction set, but also what might be needed for things like the x86 instruction set, which is a lot more complicated. There are a lot more instructions, and there's variable length instructions. As you can see, we have many, many keywords today. Fortunately, I'm not going to list them all. So what are we going to be covering in this lecture? So we're going to introduce what a processor is. We're going to need to build a couple logic design conventions. We're going to talk about the data path, something that we mentioned in chapter 2. We're going to look at how we can simply implement a processor. So what are the basics that we need if we wanted a processor? We're going to go over if we want to make a processor a little bit faster and exploit some of the parallelism in there. We can do this through pipelining. However, we'll notice that pipelining introduces a couple more little things we have to be wary of. And so we'll look at the pipeline data path and control, as well as data hazards. And then what our penalties are for sometimes we can forward data that isn't quite finished yet, but then other times we have to just stall and wait for something to finish. We'll look at other things such as control hazards, what happens with things like exceptions, and then we'll go into a couple more advanced topics like parallelisms via instructions. So this is going to be that instruction level parallelism. And then we're going to look a little bit at the ARM Cortex-A53 and then the Intel Core i7 pipelines. So pipelines of things that are in practice, not just say the RISC-V pipeline that we might be designing in this book. So something that's a little more complex. And then we might take a little bit of a look into some optimizations we can do for ILP, specifically with matrix multiply. Matrix multiply is a very, very common thing that you want to speed up because it's a foundation of a lot of linear algebra and therefore a lot of machine learning. They have some more stuff in here that we might skip over, which is an introduction to digital design using an HDL, a hardware description language. So we might skip over some of this, but of course we have to always cap off on fallacies and pitfalls, or pitfalls and fallacies, a classic of any Hennessy and Patterson or Patterson and Hennessy book. So where are we starting? So we're focusing right here today. So memory will, I think, be in the next chapter. I think in a chapter or so after that, it'll go over input and output. But we really want to talk about control in the data path because we're talking about the processor today. So in chapter 1, we saw that we generally measure performance by a number of factors, and one of the typical ones is clock cycles per instruction, or CPI. In chapter 2, we saw that the compiler in the instruction set architecture determined the instruction count required for a given program. So how good our compiler is will determine how many optimizations it can do to potentially, say reduce instructions or find little ways out to make things quicker. But at the end of the day, the compiler and the instruction set is what really determines what our instructions are and how those get formatted, at least before we hand them over to the processor. However, the implementation of the processor determines both the clock cycle time and the number of clock cycles per instruction. So this just says that the clock that we're running off of is a hardware element, and then the number of clock cycles per instruction is determined by the architecture. So these are things that are fixed that we can't change. So in this chapter, we construct a data path and control unit for 2 different implementations of the RISC-V instruction set. So this is an important thing. This is where computer architecture research really is. We may be limited on things like, okay, well, maybe our clock cycle can't exceed this, but we can build different pipelines. We can build different control units and data paths that may make some things faster, some things slower, and so we weigh those trade-offs. Okay. So we'll, of course, look at a more realistic pipelined RISC-V implementation. And then we'll have the necessary background after this to at least understand how things like the x86 architecture work. Okay. So for the reader interested in understanding the high-level interpretation of instructions and its impact on program performance, the initial section on 4.5 presented the basic concepts of pipelining. Current trends are covered in 4.10. Okay, so this is just a breakdown of this chapter. Okay, so let's look at the basic RISC-V implementation. So these are the things that we're going to be constrained on. So memory reference instructions, load double word, and store double word. We have to support things such as add, subtract, and an OR. And we at least have to support something such as the branch if equal. So in order for us to have, a semi-functional processor, we at least have to be able to take things in and out of memory. We have to be able to do some basic operations, adds, subtracts, logical operations like and OR. And then we have to be able to jump around in the program. So we at least need something like a branch if equal or conditional branch. So of course this subset doesn't include all integer instructions. So things like multiply, shift, and divide are in here. And it also we don't talk about those floating point instructions that we saw earlier. But those aren't exactly necessary for, a very simple data path. We don't necessarily need to design a processor that takes the IEEE 754 standard instructions. Sometimes we can just say, okay, let's just see the very basic case if we just want an add. The other reason is, to implement these things, it's more or less trivial work. It's not something that we really need to flesh out too much. We just kind of build on the same principles that we already have. Okay. In examining the implementation, we'll have the opportunity to see how the instruction set architecture determines many aspects of implementation. So we'll see how we design this processor affects things such as CPI, which remember is clock cycles per instruction. We'll also look at things such as simplicity favors regularity. So if we design our processors in a very, very complex way, then they may not be scalable for the future. Okay. So now we can look at an overview. An overview of the implementation. So in Chapter 2, we looked at the core RISC-V instructions. So we remember from that last lecture, if you haven't seen it, you can go ahead and go up on YouTube. It's linked below. Everything's posted there. And we talked about things like the integer arithmetic, logical instructions, the memory reference instructions. So for every instruction, though, we always have these two steps. So this is going to be, we're going to send the program counter, whatever that value is, whatever the PC value is, to memory. And this is how we're going to fetch our instructions. So we fetch our instructions from something that we generally call instruction memory. Then next, we usually read one or two registers. So based upon those fields that we saw that we could break down assembly instructions into a series of bits, and those bits typically held, whether it was an immediate value, such as just a numeric value like 20, or if it was a value that pointed to a register, so say X3 or X4, X5, or maybe even the constant 0 register X0. So for the load so for some instructions we need multiple registers. So if we're adding two registers, we would need to access two registers in order to add them. But if we're just doing something like a load, we actually only need one register, because we really just need to look up the memory address that we're trying to load a value from. So after these two steps, the actions required to complete the instruction depend on the instruction class. So we saw that in Chapter 2, we could break down these instructions into a couple different categories. And so typically these are the memory instructions, arithmetic instructions, and branches. So things that grab stuff from and put stuff in memory, things that do some sort of mathematical operation like adds and subtracts, and then things that jump around in the code, so that change the program counter value, and we call these branches. Okay, so we can move on here. For example, all instruction classes use the ALU, the arithmetic logic unit, after reading the registers. The memory reference instructions use the ALU for an address calculation. So whether we're adding, say, two numbers together from registers in an add instruction, or we're trying to access something from a certain pointer value in memory, we still need to use the ALU. So after using the ALU, the actions required to complete various instruction classes differ. So one of the big differences, so for a memory instruction or a memory reference instruction, we need to go to memory. So we need to access memory. So either reading or writing to memory. But for something that's just an arithmetic instruction, there's no point for us to go to memory. So typically, we just need the data coming out of the ALU, so the result of, say, an add, and we need to write it back into, say, a register. I don't think the RISC-V instruction set supports writing directly to memory. I'm pretty sure that's the case. Lastly, for conditional branch instructions, so we already went over memory instructions and arithmetic instructions. So we have conditional branch instructions, so we're going to be looking specifically at branch if equals. So we may need to change the program counter, the next program counter. So in the memory ones, what we did were we got some address, we calculated that with the ALU, and then we did something with memory. Either we loaded some value or we stored some value. With the arithmetic instructions, we passed two values to the ALU, and then we wrote back into our register file some other value that we calculated. But with the branch instructions, we do some calculations. So generally we're going to check an equality, at least in this case, and then we're going to take that result, and that's going to change the program counter this time, not necessarily something in the register file or memory. So figure 4.1 shows a high-level view of the RISC-V implementation, focusing on various functional units and their interconnection. Although this figure shows most of the flow of the data through the processor, it omits two important aspects of instruction execution. So let's see what we have. So we start here at the program counter. So the first thing we do is we have this program counter is used to address some instruction in instruction memory. That instruction comes out of the other side of instruction memory, and this looks up any registers that we need to. Maybe it passes a value directly to the ALU. Then the ALU does some kind of number crunching. If we're simply doing something like calculating an address, we go directly to data memory. However, if we're just doing some calculation like an arithmetic instruction, we may just write this back immediately to the register file. And then otherwise, if we say have a branch instruction, we may go here, take the original PC that we're at, add some offset to it that we get from the instruction, and then that becomes our next PC value. So this is how we handle branch instructions. So branch instructions are so we'll go ahead and do this is going to be branch. So branch instructions are mainly going to be in this region. If we wanted something like a arithmetic instruction, we're mainly concerned with this portion of the processor. And then finally, if we wanted a memory instruction, it's just like an arithmetic instruction, except we need to include data memory in here. So we see there's quite a bit of overlap here. So we have a lot of reuse of instructions, or a reuse of these simple components. Okay. So let's see if there's anything interesting in the caption. So an abstract view of the implementation of a RISC-V subset showing the major functional units and the major connections between them. Okay, we kind of went over all of this in the previous section. So first, in several places, figure 4.1 shows data going to a particular unit as coming from two different sources. For example, the value written into the PC can come from one of two adders. The data written into register file can come from either the ALU or data memory. So what they're talking about is, if we look at this data line is connected here to the output of the ALU, but it's also connected to data memory. So we have a couple things that are cross-connected here. And then same thing right here. We have an adder right here that simply increments the program counter by 4, which basically means go to the next instruction, because we're talking about things that are words. So a word is going to be 4 bytes, so 32 bits. And so this says move forward by 4 bytes. Or we have some arbitrary value over here if we have a branch instruction, but we see that those are both connected to the same spot. So that's what they're talking about here. Okay. In practice, these data lines simply cannot be wired together. Well, of course, we can't just splice two things together and expect not to get different values or have some kind of short. So typically, we must add a logic element that chooses from among the multiple sources and steers one of those sources to its destination. So we need to multiplex them. So we use something called a multiplexer. Although this device might be better called a data selector. So we have a lot of different names for things. But typically we'll call it a MUX or a multiplexer. So Appendix A describes the multiplexer, but all we really need to know is that we need to have some kind of control line that's going to select which input we're taking. And so the control lines are set based primarily on information taken from the instruction being executed. So after we get that instruction from instruction memory, we typically have enough information to set all of the control logic. So the second omission, besides these data selectors or multiplexers, is that several of the units must be controlled depending on the type of instruction. For example, the data memory must read on a load and write on a store. So we didn't have any defining features in here for, say, reads and writes. So data memory just sees an address and it sees data. So we actually need another port in here to say, okay, am I going to be reading out data, or is someone going to be writing data to me? So what else do we have? So figure 4.2 shows the data path with the 3 required multiplexers added, as well as control lines for the major functional units. A control unit, which has the instruction as an input, is used to determine how to set the control lines. Okay? So let's see, it's a slightly more complicated version of the processor that we just saw. However, we see that the fundamental structure is still here. So what's changed? Now, we see that now we have to determine whether or not we're going to be simply incrementing the PC by 4, or if we're going to be taking some new branch address. Then we're going to look here. We now have 2 different lines here. One for if we're getting a read into data memory, or if we're getting a write to data memory. We have a specific line telling us, hey, am I trying to write back some value to the register file, or am I just reading values out? What else do we have here? We have the ability to either send something directly from instruction memory to this ALU, or take a value from the input of a multiplexer. This stays the same. We can just tie the register file to the ALU because we know we need, for every instruction, we're going to need at least one register, at least with our current setup. And then we have right here, because we're doing a branch if equals, we have a 0 line coming out from the ALU, ANDed with this branch line from the control unit. So the control unit is what's going to determine all of these things. So the register write, mem read, mem write, ALU operations, and this branch line is going to, this control unit that takes the instruction from here as an input, it's going to determine all of this. So we add a couple things. We make it a little more complicated, but the fundamental structure is still there. So in the remainder of this chapter, we're going to refine this view to fill in the details, which requires that we add some further functional units. So we have an okay model right now, but we'd like to make it better. So sections 4.3 and 4.4 describe a simple implementation using a single long clock cycle for every instruction. So this is what we call a single cycle processor. This is not what we use today. This is actually we find to be very, very slow. And then I think we look at multi-cycle processors. We must, because I know we go over pipeline processors. Okay. So here it basically says, while a single cycle processor is easy, it's not practical. Okay, we'll jump directly to a pipelined implementation. So the main difference between a pipelined implementation and a single cycle implementation and say a multi-cycle implementation, between that of the pipelined and the multi-cycle, they're very, very close. So we can just skip over that. So now let's look at some logic design conventions. So these may be familiar if you tuned in last Friday when we started the logic design textbook, but if not, this will be a good review. So to discuss the design of a computer, we must decide how the hardware logic implementing the computer will operate. So of course we need to decide how the computer is going to work. So we're going to review some key ideas here. And so Appendix A, if you have the book at home, that might be a good place to start. But we'll go ahead and move ahead. We're going to assume a little bit of knowledge, but I'll try to clarify some stuff as we go along. So the data path elements in the RISC-V implementation consist of two different types of logic elements. So elements that operate on data values, and then others that contain state. So we call things that operate on data values combinational, which means that their outputs only depend on their current inputs. And then the other ones we typically call sequential. Sorry, this is combinational. Sequential ones we generally say depend on not only the current inputs, but the previous inputs or some state prior to this. So we can consider something that's as simple as an operational element like an AND gate or an ALU. We saw that these can be made by just combining a bunch of gates together. We call these combinational elements. Now let's talk about state elements or sequential elements. So other elements in the design are not combinational but contain a state. An element contains a state if it has some internal storage. So we need to be able to store some kind of state and remember it. So typically we just say that it has some kind of memory to it. And so we're going to call these state elements. And so a key thing to kind of, wrap your head around this is that if we say pulled the plug on this computer, well, we could restore some values because it saves some state elements. And so it'd be like we never lost power. If we had something combinational and we say shut it down, when we turn it back on, we have no guarantees about what values will be where. Okay. And so two typical state elements are things like registers and memory. Okay, a state element has at least two inputs and one output. The required inputs are the data value to be written into the element and the clock. So the only things that really run off of clocks are these state elements. Things like, an adder may not run off of a clock. It may just be a combinational design that we may clock on both sides of it So we may stop the output so we don't lose the output, but as far as the entire adder design, we don't necessarily clock that. So for example, one of the logically simplest state elements is the D-type flip-flop, which has exactly two inputs, a value and a clock, and one output. In addition to flip-flops, our RISC-V implementation uses two other types of state elements, so memories and register. So we have instruction memory, and then we also have data memory. So logic components that contain state are also sequential, because their outputs depend on both their inputs and the contents of their internal state. So for example, the output from the functional unit representing the registers depend on both the register number supplied and on what was written into the registers previously. So we can consider the register file a sequential element. So now let's talk about clocking. So everyone's familiar with, what frequency their processor is running at. Everyone seems to care a lot about, higher numbers are better, which isn't always true. Case in point, the Pentium 3 versus the Pentium 4, where the Pentium 4 I think was clocked at around 1 gigahertz. The Pentium 3 was clocked at 750 megahertz, but in reality, the Pentium 3 was actually better or faster than the Pentium 4, because the Pentium 4 introduced, I think, a 22-stage pipeline versus the 14-stage or so that the Pentium 3 was, and it just introduced this wild overhead that was pointless. So that's a case where a lower clock speed was actually faster. So now let's talk about clocking a little bit. So clocking methodology, we consider this the approach used to determine when data are valid and stable relative to the clock. So we're really cared about stability when we're talking about sequential circuits. So a clocking methodology defines when signals can be read and when they can be written. It is important to specify the timing of reads and writes, because if a signal is written at the same time that it is read, the value of the read could correspond to the old value. So this is saying that if we do two things at the same time, there's no real guarantee of which will come first. And if you've ever had any experience with multi-threaded applications, this may ring some bells with you. So computer designs cannot tolerate such unpredictability. Clocking methodology is designed to make hardware predictable, so we want to be smart with our designs. So for simplicity, we will assume an edge-triggered clocking methodology. So this means that we will only do certain actions on either, if we look at this picture right here, and if I can find my cursor, there it is. We will only do certain actions, say, on the rising edge of the clock, or maybe the falling edge of the clock. So we'll pick one of these and we'll only do changes on that one edge. Okay. An edge-triggered clocking methodology means that any values stored in a sequential logic element are updated only on the clock edge. So we only do things on the clock edge. Because only state elements can store a data value, any collection of combinational logic must have its inputs come from a set of state elements and its outputs written into a set of state elements. The inputs are values that were written in a previous clock cycle, while the outputs are values that can be used in the following clock cycle. So let's say that we have this state element 1 that's feeding this combinational circuit. So let's just call this, for simplicity, we can just call this an adder. So the first clock cycle hits, we'll assume a rising edge clock. So we're not going to do anything on this clock edge. The next time we do something is on this rising edge. So we go from a logic 0 to a logic 1. So what we're going to do here is, this is going to be continuously feeding some value to this combinational logic. And it's going to do that all the way here. So the combinational logic across this entire time is going to be churning. It's going to be calculating some numbers, doing whatever it needs to do, until maybe it finishes here. So the outputs are set. We know our outputs that we're feeding into this state element. However, we don't actually write them until we get all the way here. We hit another rising clock edge. All of our outputs here get saved by this state element and may be forwarded through to the other side. These inputs change now, so they may be a new set of inputs. But we saved these outputs. Okay. The highlighter back. There we go. So we already went over figure 4.3. So what's a control signal? So a control signal is a signal used for a multiplexer, selection, or for directing the operation of a functional unit. So this contrasts with a data signal, which contains information that is operated on by a functional unit. So if we go back to this original figure here, or one of these original figures, we can see everything coming from this control unit in blue. We'll call that a control signal because it determines if we're going to do a memory read or a memory write, while we'll have data signals here in black. So the value coming from a register is going to be a data signal because it only contains data. It doesn't control anything. Okay. So typically we use the word asserted to indicate that something is logically high or a 1. And we'll say deasserted to represent logically 0 or low. So an edge-triggered methodology allows us to read the contents of a register, send the value through some combinational logic, and write the register in the same clock cycle. And so figure 4.4 gives a generic example. It doesn't matter whether we assume that all writes take place on a rising clock edge or on the falling clock edge, since the inputs to the combinational logic block cannot change except on the chosen clock edge. So here we see that if we have, say, some input, let's go ahead and get the pencil back out. If we have some input coming in, we're going to make our way all the way out, and this will feed all the way back around as the next input. And so after we get here, we'll make this blue now, because red was something, red was some value, but then on the other side of the combinational logic, we'll have a different value. So what happens is, on the clock edge, this value that we already calculated gets trapped by the state element. It gets put to the other side, and it starts over again. And then on this next clock cycle, if we use green to represent the next item, we see that it does take some time to go through this combinational logic. So we don't have to worry about just completely overwriting our initial value immediately. We see that we have some time, there's some delay going through this combinational logic, so we can guarantee that the state element is going to get the correct value. Okay, so let's continue on. Let's get the highlighter back out. Any questions on anything so far? I know this is a lot of stuff to take in, but hey, we're learning about processors for the first time. This is pretty cool, isn't it? So for the instruction set that we're working with, which is going to be RISC-V, the 64-bit RISC-V architecture, nearly all of these states and logic elements will have inputs and outputs that are 64 bits wide. since that is the width of most of the data handled by the processor. So we want to make this regular. We don't want to have a bunch of variable size lines running through the processor. So sometimes it's just easiest to make it all 64 bits wide. Now, in some cases, this isn't true. In other cases, it is. DeckMac11, hey, thanks for the follow, man. I appreciate it. We're having a great time today. Okay, and so we typically call these things, so we will make it clear whether a unit has an input or output that is other than 64 bits wide. So the figures will indicate buses, which are signals wider than 1 bit. So whenever we're talking about something wider than 1 bit, we're going to call it a bus. So at times, we will want to combine several buses to form a wider bus. For example, we may want to obtain a 64-bit bus with two 32-bit buses, so we may splice these together. So in this case, labels on bus lines will make it clear how we are concatenating or combining buses. Arrows are also added to help clarify the direction of flow of data between elements. And then color indicates a control signal contrary to a signal that carries data. So this will be more important when we start looking at diagrams. Okay, so check yourself, true or false. Because the register file is both read and written on the same cycle, any RISC-V data path using edge-triggered writes must have more than one copy of the register file. Okay. So we already saw that we only need a single, that we already saw that this is false, and we already saw why. We saw that things can be read and written on the same clock cycle, even with edge-triggered writes. And that was because of that delay idea that we were talking about. So a little elaboration, there are also 32-bit RISC architectures. And naturally enough, most paths in its implementation would be 32 bits wide. So this goes back to that same idea that we've been kind of stressing over and over of regularity. So if we make something that works in 32 bits, we might get lucky enough that we may just be able to scale things like the buses and the number of ports on things like the register file to 64 bits, and we're fine. Other times we don't get so lucky, but in many cases we can if we make a good design. So now let's talk about the data path. So a reasonable way to start a data path design is to examine the major components. So let's start looking at which data path elements each instruction needs. And so that way we can work our way through abstraction instead of having to tackle this all at once. And so what do we consider a data path element? This is just a unit used to operate on or hold data. So it operates on or holds data within a processor. So in the RISC-V implementation, these are going to be things like the instruction and data memories. These both hold data. The register file, that also holds data. And then the ALU and adders, these operate on data. So this is going to make up our data path elements. And then we have, of course, our program counter that we talked about previously, which is a special register containing the address of the instruction in the program being executed. So we see that 4.5a shows the first element needed, a memory unit to store instructions of a program and supply instructions given an address. So we call this the program counter. So here we have our two state elements that are needed to store and access instructions. So of course we're going to need an instruction memory. This is what's going to store all of our instructions. We need a program counter. We use this value to address this instruction memory. And then we have to have an adder here. And this adder will help us to cycle through instructions. So we can think of it as, okay, we have a PC value of 0. This goes to the instruction address up here. we fetch an instruction, and then that goes to the rest of the pipeline. Now the PC value goes to this adder, and then we may put a constant. If we're talking about something very simple, we may just put a constant 4 in here, and this will be fed back to the program counter so that we cycle to the next instruction on the next cycle. So this is the most simple way that we can think about a program counter and how we would actually fetch instructions and then decode them. Okay. Let's see. So next we're going to talk about how do we execute these instructions that we're fetching. So to execute any instruction, we must start by fetching the instruction from memory. So that's what we talked about here. To prepare for executing the next instruction, we must also increment the program counter. We talked about that as well. So here's how we can assemble those three components. So we have some program value, or program counter value that reads an address. We get an instruction out. This just goes to the rest of the pipeline. Put it in red. Then we take this program counter value, we increment it by 4, and then this will become the address of the next instruction. So as we saw earlier, this gets a little more complicated if we have, say, branches that aren't the next instruction but maybe behind the previous program counter value or farther than one instruction away from the program counter value. So we'll have to change a little bit to handle branches, but if we're just doing things in order, this works pretty well. So now we need to consider our format instructions. So these are typically register type instructions. So we're going to be calculating or working on data for the most part here. So they all read 2 registers, perform an ALU operation on the contents of the registers. So we're not doing any, these registers don't hold memory addresses that we're looking at something in memory. They hold values that we're calculating or we're doing some calculation on. And then we write the result to a register. So these are typically R-type instructions or arithmetic logical instructions because they do arithmetic. So examples are just exactly the ones we saw earlier, and or addition, subtraction, logical and logical or. So we talked about those in chapter 2. So then let's talk about the register file. So this is just another state element that is a set of registers that can be read and written by supplying a register number. So very similar to memory, but typically smaller and faster than memory. And so for the processor that we are working on, so this RISC-V architecture, we assume that we have 32 general purpose registers inside of this structure that we call a register file. So as we said also, we need an ALU for these R-type instructions. So we also need to talk about the R format instructions, that they're going to have 3 register operands, 2 that are inputs, 1 that's for storing the result. Okay. So let's see, for each data word to be read from the registers, we need an input to the register file. So we need 2 inputs and then, or 2 outputs and then 1 input. So we need to read 2 registers and then write 1 register value back. So we're going to need 3 input lines here. And then we're reading 2 registers. And then of course we have to have some control signal to say, hey, are we writing some value back to the register file? Because we're not always writing to the register file. Okay? So our inputs over here on these reads and write registers is going to be the register number, and this is going to be decoded by whatever instruction comes in. So it's also important to specify that these inputs are 5 bits, and that's because we said that our instruction set has 32 registers. So in order to represent the number 32, or 0 to 31, which is 32 different values. We need 2 to the 5th. So we need 5 bits. So 1, 2, 3, 4, 5. Okay. Let's go ahead and move on. So figure 4.7b, which is this ALU that we saw, there's nothing too special here. We have a couple of inputs, we have an output, and then we have a line here that we see is 4 wide, and this is just to determine what operation the ALU is doing. But nothing too fancy here. We just take some inputs and we calculate a result, or sometimes we check if it's a 0 result. That's generally a special number for us, especially if we're doing things like branch if equal. Okay. So we saw this ALU with 64-bit inputs and a 64-bit result, as well as a 1-bit signal if the result is 0. The 4-bit control signal of the ALU is described in detail in Appendix A. So the main thing that we need to know about this 4-bit control signal is that it'll just determine, hey, are we doing an add? Are we doing a subtract, an and, or an or? So now let's consider the RISC-V load register and store register instructions. So we have this general form of load x1, some offset of x2. So this says that we're going to look in memory at the address that's held by x2 with some offset, and we're going to store this value into the register x1. Or with this store instruction, we're going to store the value held by x1 into the memory location held by x2 with the offset, just offset here. So offset maybe 12, 16. So these instructions compute a memory address by adding the base register to the 12-bit signed offset field. If the instruction is a load, the value read from memory must be written into the register file in the specified register. So we're going to need both the register file and the ALU. So we saw for register file type instructions, we just needed the register file and the ALU. Now for these memory instructions, we need the register file to provide the address. We need the ALU to do some calculations for the address, and then we need the memory itself, the data memory itself, in order to get whatever value is stored there. Okay. Sign extend. So these are just some basic terms that are good to know. So to increase the size of data, replicating some higher order data, we didn't generally do something like sign extension. So say if I had a number, I had the number 3. So I had 0, 1, 1 in binary. Now, say I needed 4 bits. Say I had a bus that was 4 wide. So I needed another bit here. So with sign extension, it says I can take whatever the sign bit is and extend it out as many times as I need to, and the number will stay the same. So for positive numbers, it's very easy to see this. If we add a 0 here, we still get the number 3. Now, let's take another case. Let's take -1, for example. So for -1, we get 1, 1, 1 in 3 bits. So this is -4 plus 3 plus 2, -1. Okay, now what happens if we do sign extension here? So we add a 1. This is no longer the sign bit, so it becomes a +4. However, we have a larger negative number out here. So this will be -8. Well, what do we get? Negative 8 plus 4 is negative 4 plus 3 plus 2. So we saw that doing sign extension, we really didn't change anything. This is still negative 4 plus 3 plus 2. And so we can actually extend this as many times as we want, and this number will always be negative 1. Derek, engineering today. I haven't followed these streams, but is there any point to learning RISC nowadays? I think there's a point to learning RISC. It's a reduced instruction set architecture, which is typically popular. If you look at something even like x86, x86 is a complex instruction set architecture, but at the very low level, x86 processors don't operate on x86 instructions. x86 is actually translated down into a RISC-like instruction set. So if you get down a RISC instruction set, there's tons of things that you can look at. The ARM instruction set isn't a CISC instruction set. So there's a good value in it. And I mean, this is RISC-V, right? This book was published very recently, and it's being taught everywhere because it's the Patterson and Hennessy book. So there's fairly good motivation to learn something like RISC. Good question. Good question. Okay. So we talked about sign extension. So that'll be something like this. We'll have some unit where we may only get from our instruction, like we saw previously. Our instructions are only a certain size. So we only have so much space to store values, and so we can't store, say, a 64-bit value if the instruction is only a total of 64 bits, because then, okay, where's the rest of our control information going to go? How are we going to know what instruction to execute? So generally we have sign extension units where we may take a 32-bit bus and we may sign extend it to something like a 64-bit value. So here we'll take something that's, say, 000111, and we may extend it out as many times as we need to in order to get it to 64 bits. Okay. So these are the two units that we need for loads and stores. We need some ways of, let's see. We need some way to generate an immediate value. So as we saw here, where is it? As we saw from these instructions, we saw that there is some offset value here that's typically embedded in the instruction. Now we need to make sure that that's a 64-bit value, so we need to sign extend it. We need to, say, add this in the ALU with whatever address we get out, and then depending on if it's a read or write, we'll use this control logic for memread or memwrite, and our data will come out the other side, or we'll just write the data in. Okay. So now let's talk about branching. So we've talked about R-type instructions. We've talked about R-type instructions, which are typically arithmetic instructions. We've talked about memory-based instructions, but now let's talk about branching instructions. So specifically in our reduced instruction set, we're going to be looking at only the branch if equals instruction. So it has 3 operands, 2 registers that are compared for equality. So if we say branch if equal, we have to compare 2 things. And then a 12-bit offset used to compute the branch target address. So this basically says if these 2 registers are equal, don't add 4 to the program counter, add whatever this 12-bit offset is to the program counter. So to implement this instruction, we must compute the branch target address by adding the sign extended offset field. Remember, we want to make a regular design, so we have to extend this 12 bits to, say, 32 or 64 bits, because that's what all of our other data is. So the things we have to pay attention to: So the instruction set architecture specifies that the base for the branch address calculation is the address of the branch instruction. So this just says that what we're doing an offset of must be our current program counter value. And the architecture also states that the offset field is shifted left 1 bit so that it is a half word offset. This shift increases the effective range of the offset field by a factor of 2. Okay, so this just says that we can't jump at very, very tiny granularities that don't make sense to us, so we shift it left by 2. To deal with the latter complication, we will need to add this left shift operation. So we'll probably just add some simple buffer that shifts it over. Okay. So as well as computing the branch target address, we must also determine whether the next instruction is the instruction that follows sequentially or the instruction that is the branch target address. So we don't want to waste a bunch of time calculating some value that turns out to be wrong. So typically we can calculate both of these values, the next PC as well as the branch PC, in parallel. And then we can use the control logic to say if the branch is taken or if the branch is not taken. Okay. So thus the branch data path must do 2 operations. So that's exactly what we just said. It must compute the branch target address and test the register contents to see if we're going to use that. But we also want to compute the next address. So we're just going to use the ALU for the compare, and we're going to use the 0 output from the ALU for that. And then later on, we're going to show how do we connect the control signals of the ALU for this data path. So this is the basic idea. We're going to take some immediate value, which is going to be the offset from the instruction. We're going to compare 2 registers and see if the output is 0. Now, we'll have our normal register file data path out here. But over here, we're going to take this immediate value, we're going to add it to the current PC value to find where the branch target is, so the target address or the target instruction we want to go to if this is 0. And then this is going to tie into our original data path, which, let's see, is it over here? It's not over here, but we saw this previously, and we'll probably see it again. So now that we've kind of built up these individual components, we've built up how to do R-type instructions, how to do M-type or memory type instructions, and how to do branch type instructions, we can now move on to creating a single data path. So let's see, building a data path. Example. The operations of arithmetical logic units, R-type instructions, and memory instructions data path are quite similar. The key differences are, for arithmetic instructions, the ALU operation is done using 2 registers. The memory instruction can also use the ALU to do address calculation, but the second input is the sign extended 12-bit offset field. So we're only using 2 registers for arithmetic instructions. For memory instructions, one of the registers is going to be used for an address, but then we're going to have an immediate value embedded in the instruction for the offset. So the value stored into a destination register comes from the ALU for an R-type instruction, or the memory for load. And then it says show how to build a data path for the operational portion of the memory reference and arithmetical logic instructions that use a single register file and single ALU to handle both types of instructions. So the answer here is in figure 10, and we can go over it a little bit. So we see that it's pretty much the same of what we've seen before. The only difference is we have a couple more pieces of control logic. So one, we have to use an additional multiplexer to determine if it's a memory instruction. We want to be using this immediate generation, this sign extension. But if it's an R-type instruction, we want to just be reading out a register. What else do we need to add? We also need to add another multiplexer here. And this is going to determine, okay, so if it's an R-type instruction, we really want to bypass data memory. So we want to use this ALU result, and mem to reg is going to want to be 0, so we can just bypass this entire data memory structure. On a memory instruction, we want this mem to reg to be 1. That way, we get this read data to go back to the register file. So for something like a load. Okay. Very good, very good. Now, if we add all these things together, we get this simple data path for the RISC-V architecture for all of the 3 instruction classes that we covered. So we see that we can handle branch type instructions. So we have this additional immediate value generation is hooked up also to calculate the branch target, and we can select whether or not we're going to be using just the next program counter value or we're going to be using the target value. We see we have the same mem to reg and ALU source controls that determine whether or not we're doing a memory or we're doing an R-type or arithmetic instruction. And so we've built a fairly simple processor. And so for all intents and purposes, this is a simple processor. It's what we call a single cycle processor. We don't have any buffers in here or anything to determine or to split up the instruction across multiple clock cycles. Simply, the program counter gives some value and all of our inputs trickle through this entire pipeline all at once. Okay. So let's talk about a simple implementation scheme. So in this section, we'll look at what might be thought of as a implementation of our RISC-V subset. So remember, we're doing 4 arithmetic instructions, we're doing loads and stores, and we're doing a branch if equal. Okay, so what do we need for ALU control? For ALU control, we really only need 4 things. We need the ability to do ANDs, the ability to do ORs, adds, and subtracts. So we're going to use 4 bits for this. So depending on the instruction class, the ALU will need to perform one of these 4 things. Okay. So we'll get this value. This will be something that's encoded in the instruction itself, and then our control logic will create these values. So we can generate the 4-bit ALU control input signal using a small control unit that has inputs, the func7 and func3 fields of the instruction. So if you remember from the previous time when we talked about all the different fields, we saw that there are fields for registers, there are fields for immediate values within the instruction. We see that we can also embed whether the operation in here. So for things like loads and stores and branches, this func7 or function7 field can be any value because it's ignored. But we see that for things such as and or sub or add sub and or, what these contents are actually matters. So this is typically something like an opcode. And what we mean by an opcode is this is going to determine what operation we're doing. Hey Lev, thanks for the 105 bits, man. I'm sure you had to watch a lot of ads for that. I appreciate your dedication to the cause. You are 1/3 the way helping me to buy a cup of coffee today. Are any of the things actually popping up? The notifications? I hear the sound, but I'm having to do some screen capture thing that's kind of messy. Well, hey, Lev, you're number one cheer donator. You're number one in my heart. Thanks for being here today. Okay. So let's move on. What else do we have today? So we talked about how we would, or where we're getting the information to determine whether or not it's one of these arithmetic instructions, but how do we actually figure this out? So we can use something called a truth table, which if you join me on Fridays for the logic design lecture, you'll figure out how to use truth tables in no time. So a truth table from logic, a representation of logical operations by listing all values of the inputs, and then in each case showing what the resulting outputs should be. So in this case, we want these values for certain series of inputs, and we put X's for don't cares. And so this is just an easy way that we can typically use to reduce logic by hand. Or, even a lot of times we'll just throw this into a computer and it'll do it for us. It'll do some reduction technique. So as I said earlier, the X's are don't care terms. So all of these are don't care terms. This means that they can take on any value, a 0 or a 1. It doesn't matter. We're just going to ignore them. And so this is important because they can be an arbitrary value, a 0 or a 1. We can typically use them in this case to reduce logical expressions, because sometimes it's easier if things are 1s or things are 0s, if we're doing things like Boolean algebra. So now let's talk about designing the main control unit. So now that we've described how to design an ALU that uses the opcode and a 2-bit signal to control inputs, we can return to looking at the rest of control. So we don't just want to control what operation the ALU is doing, we need to generate all of those other signals. So we need to determine if we're doing a memory read, a memory write, a register read, a register write, whether we're branching or not, etc., etc. Okay. So to start this process, let's identify the fields of an instruction and control lines that are needed for the data path we've constructed previously in figure 4.11. So here we have the different instruction types, R, I, S, and SB. Let's see, so this is going to be a register type instruction. This is going to be an immediate type instruction, so this will be a register and an immediate value. And then we have these S type instructions, which have immediate values. What's SB going to be? I'm not sure what SB is actually. Okay, so S is store. And it looks like SB is store byte conditional. Okay. So opcode is what we were talking about earlier. This is going to be the field that denotes the operation and format of an instruction. So when we're talking about opcodes, this is just determining what the processor is going to do. So we already saw this in chapter 2. It's always bits 6 to 0, depending on the opcode. The function 3 field, 14 to 12, can make up part of the opcode, as well as the function 7 field, bits 31 to 25. So you see that we don't always have, say, all the opcode bits in a row. Sometimes they're kind of disaggregated, they're spread out. So here we have 7 bits at the very bottom. In the middle someplace we have another couple of bits, so another 3 bits here. And then we have another, let's see, this is going to be 7 bits, I think. Yeah, another 7 bits here. So the first register operand is always in the bits positions 19 to 15. So it's always going to be these 5 bits. Remember, it's 5 bits because we need to address 32 different registers in the RISC-V ISA. If we had more instructions, if we say had 250, or if we had more registers, like in NVIDIA's GPU architectures, where every thread has 256 private registers, we would need a minimum of 8 bits. Or would it be 9 bits? It'd be 9 bits. But it's okay, they use 32-bit instructions. Okay. So the second register is always bits 24 to 20. So we can also have another operand that can also be a 12-bit offset. And then the destination register is always in the bit positions 11 to 7. So remember, another 5 bits here. So the first design principle, simplicity favors regularity, pays off here in specifying control. So using this information, we add the instruction labels to the simple data path, show these additions plus the ALU control block. So let's just go ahead and take a look at the data path and what we see. So now we take some 32-bit instruction, we break down where each part goes, so we're going to give the entire 32-bit instruction to the control. That way it knows what it needs to, it can calculate whatever the ALU operation should be. But we only give the register, we split off different parts of the instruction that are for addressing the different registers. So we already said that register 1 is always going to be, say, 19 to 15. Bits 19 to 15, that is. This register 2 is always going to be bits 24 to 20. And say this register 3 is always going to be bits 11 to 7. So we've kind of just added which bits we're using from the instruction for each of these things. Okay, so let's talk about what we can do with each of these control signals now, or when they need to be asserted or when they need to be deasserted. So for something like register write, if we deassert it, nothing happens. So if it's 0, it doesn't affect anything. However, when it is asserted, the register on the write register input is written with the value of the write data input. So if we put it high, we're going to write something. Then we have ALU source. So if this is deasserted, the second ALU operand comes from the second register file output. So if we look here, if ALU source is 0, we get our information from the register file, but if it's 1, we use an immediate value. Sign extended, of course. If we look at the PC source, if it's deasserted, meaning 0, we're just going to be used the next value of the PC, which is PC plus 4. The PC, when it is asserted, the program counter value is replaced by the branch target. So let's look at PC source. So PC source up here, if it's 0, we're just going to use the simple next program counter value. But if it's 1, we're going to use the target value calculated by this adder. Now, memread and memwrite, neither of them do anything if they're 0. However, if memread is asserted, or 1, the data memory contents designated by the address input are put on the read data output. And when memWrite is 1, the data memory contents designated by the address input are replaced by the value on the write data input. So let's go ahead and look here. So this just says if memWrite is 1, then whatever value coming in here is written to memory. And then if memRead is 1, whatever address given here is put on the read data line. So a lot of words to say something pretty simple. If we want to write data, we'll pull it high, and then we'll use the address. Otherwise, we're not going to use the address. We're not going to do anything. Same thing with, this is for write. So for write, we're going to use this address and this write data, and we're going to write something to memory. And then finally, mem to reg. That's that final multiplexer output. So if it's 1, we're going to use the value that we got from memory. If it's 0, we're just going to use the output of the ALU. So whatever the arithmetic output was. Okay. So now that we've looked at the function of each of the let's see, we're at the right spot. So now that we've looked at the function of each of the control signals, we can look at how to set them. The control unit can set all but one of the control signals based solely on the opcode. The PC source signal is the only one that can't, because this requires some calculation. So they're basically saying that we can set mem to reg, memWrite, memRead, ALU source, regWrite. We can set all of these values based upon the opcode that we get from the instruction. However, this program counter source can only be excuse me, sneezed. Excuse me, sneezed again. This program counter source value, this can actually only be asserted or deasserted if we know the result of some branch if equal, some equals operation, some output here from the 0. So that's the only one that's dependent on the calculation. So to generate the PC source signal, we need to AND together a signal from the control unit, which we call branch, with a 0 signal from the ALU. So this basically says that we just need to make sure we're only going to branch if things are equal. So generally equality, what we'll do is we will subtract 2 things to calculate equality. So we'll do, say, 3 minus 3. We'll get 0. Generally, when we calculate something like 0, it sets a flag in the ALU. That's what the 0 flag is. So we're just going to check if it's equal and if it's a branch instruction. We know it's a branch instruction from the opcode from the instruction. And so that's what we're going to use for this multiplexer. Okay. Okay. Here we just have another logic table or truth table with all of our requisite inputs filled out for every single operation and whether or not they're a don't care or not. And so we can use this to determine what the logic is going to look like inside of this control block right here. Now let's look at operation of the data path. So with the information contained in figure 416 and 418, we can design the control unit logic. But before we do that, let's look at how each instruction uses the data path. So this is for something like a regular add instruction. So we're not branching, so we never have to worry about using this target calculation. So we can first look at the program counter. So for the program counter, we're just going to add 4. It's going to be 0. And the next PC value on the next clock edge will just be PC plus 4. Then we're going to take these two register values. We're going to read them. They're going to come out here. The ALU source we're going to make sure is 0, so we get this register instead of an immediate value. We're going to take the ALU result. We're going to make sure that this line right here, this mem to reg, is 0 because we're not actually looking at memory. We're just looking at the ALU. This multiplexer is going to go all the way around to the write data port, so where we write to the register file. Then here, it's going to be whatever register we are writing to. That's another part of the instruction. So in this case, it would be x1. So this says that we're going to take x2 and x3 and then write them into x1. And that's it. I may have gotten x2 and x3 mixed up. I forgot specifically the ordering of these two, of whether this is R2 or RT or RS, but I know that this is definitely x1. This is RD, the registered destination. Okay. So now let's look at a load instruction. So a load instruction, very similarly, we don't care about this target calculation because it's not a branch instruction. Now, we're not going to be reading a second register out of the register file or reading a second register out of the register file, but we will be calculating some offset value. So we're going to make sure we select that in this multiplexer. We're going to add some address from the register file with this offset value. Now this is going to be used as an address, so we're going to calculate something out here. We are not writing any data to memory, but we are reading it. Or let's see, what kind of instruction is this? Oh, this is a load instruction. Okay, so we are getting something from memory. So we're reading some value out. This is going to go back to the register file, and it's going to be written to this RD. So do they give us an instruction here? Or nope, they don't actually give us a... Oh, here we go. So we're loading into X1 again. So we're loading into X1. So this immediate generation, or right here, this will be your offset. And then X2 holds the address. So X2 will be right here. This will be the address. So that's how it looks for something like a load instruction. And this will be for a branch instruction. So for a branch instruction, we're of course not looking at memory. So what we're going to do is we're going to take two different registers. So in this case, it will be registers X1 and X2. So we'll call this X1 and X2. We'll read them in. They will both go to the ALU. We will subtract them, see if the answer is 0. If it's 0, that means they're equal. We'll go up here. We'll set this to 1. That way we choose the output of this branch target calculation, which is this immediate value, shifted to the left by 1, and then added to the current program counter value. And then this will be written back as the PC plus offset. So previously it was just PC equals PC plus 4, but now PC is equal to PC plus offset. So finalizing control. So now that we've seen how instructions operate in steps, let's continue with the control implementation. So the control function can be precisely defined using the contents of figure 418. So figure 418 was, figure 418 was just this truth table. So we can just use that truth table to actually build the logic for that control unit that we see here. So for both this control unit and then previously for ALU control, we can just build that logic. Okay, so here they specify it in this truth table. And do they give the logic anywhere? Nope. They just say that here you go, here's the truth table to be completely specified, and now you can reduce this and put it in terms of AND gates, OR gates, NAND gates, NOR gates, any gates you want. So we saw a single cycle processor. That's what we just designed. But why don't we use them today? It seems like a fairly simple idea. If we want to keep things simple and regular, well, why don't we use single cycle processors? And it turns out they're not great when it comes to performance. Turns out there's a lot of ways that they can be improved. And so, like we said, it's too inefficient to be used in modern designs. So one of the things we need to do is we need to see that the clock cycle must have the same length for every instruction. So whether or not we're doing an instruction that's short or an instruction that's long, we have to make sure that the instruction or that the clock cycle is long for every case. We can't have a variable length clock. So in this case, the longest possible path in the processor determines the clock cycle, often called the critical path. So this basically means that on every time we're not doing the longest length instruction, we're losing time. So the penalty for using a single cycle design with a fixed clock is significant, but might be considered acceptable for this small instruction set. So historically, early computers with very simple instruction sets did use this implementation technique. However, if we tried to implement floating point unit or an instruction set with more complex instructions, this wouldn't work well at all. Because we must assume that the clock cycle is equal to the worst case delay for all instructions, it's useless to try implementation techniques that reduce the delay of the common case, but do not improve the worst case cycle time. A single cycle implementation thus violates the great idea of making the common case fast. So remember, these 8 great ideas, things like designing, expecting Moore's law, or things like Moore's law to continue, parallelizing things, using prediction, keeping in mind dependability. We don't want to break those in our designs. And we see that this single cycle processor, it breaks this fundamental idea of making the common case fast. Okay. So now that we've seen something very simple, a single cycle processor, now we can get into something more complicated and something that's a lot more similar to what we do now, which is going to be pipelining. You know, every modern architecture, i7, I think i7s have a 14 depth pipeline. I think 14 is about the sweet spot that most companies have found. There was some experimentation in the early to mid 2000s about how deep can you make pipelining before it becomes inefficient or not worth it. And so you started out with, you know, things as simple as a 5 deep pipeline. And then you moved a little bit more forward and you had things like a 10, a 12, a 14 deep pipeline. And then you went a little crazy and you had something like a 22 deep pipeline. But you have to remember that a 22 deep pipeline assumes that you have that level of instruction level parallelism. The hazards become a real pain once you have to handle them for 22 instructions in flight at the same time. And then you also have to worry about, well, I'm adding little delays in 22 different spots for each of the pipeline stages, so that gets messy. So when we talk about pipelining, what do we mean? So pipelining is an implementation technique where multiple instructions are overlapped in execution. So pipelining is universal. That's what we're trying to say. Okay. Anyone who has not done a lot of laundry has intuitively used pipelining. So the non-pipelined way to approach laundry would be place one dirty load of clothes in the washer. When the washer is finished, place the wet load in the dryer. When the dryer is finished, place the dry load on the table and fold. And then when folding is finished, asking your roommate to put the clothes away. So when your roommate is done, you start over on the next dirty load. So a better way to do this is very simple. So as soon as the stuff comes out of the washer, you can immediately put that in the dryer and put the next load in the washer. So we're overlapping two different cycles of laundry there. So here we have an idea of a non-pipeline approach where we have washer, dryer, fold, put away. And then on the next cycles, we do the same. However, in the pipeline approach, we can utilize all the functional units at the same time. So after the washer is done, we put it in the dryer. But now the washer is free, so we can start another load. Then the same way, when we're folding, the dryer is now done. So we can put that in the dryer. This washer is now done, so we can use the washer again, and over and over and over. And so here we see, this maximal critical length right here, where we hit the maximum level of overlap that we can, which is we're using all four things at the same time. So at say like 8 p.m., we're putting things away, we're folding laundry, we have something in the dryer, we have something in the washer. So that's this maximum level of efficiency that we can achieve when we do pipelining. Okay. So the pipelining paradox is that the time from placing a single dirty sock in the washer until it is dried, folded, and put away is not shorter. So we're not increasing for a single instruction. We're not improving its latency. We're not making the clock faster so that it gets done faster. So the reason why it's faster is that on every single cycle here, starting at 8 p.m., we have a load of laundry being put away, rather than the previous idea, every 4 hours we had something being put away. So it improves throughput, not latency. If all the stages take about the same time and there is enough work to do, so this is important, this goes back to if there's enough parallelism, then the speed up due to pipelining is equal to the number of stages of the pipeline. In this case, 4. So here we get a 4x speed up. So we did this in 4 hours versus here we did it in 16 hours. Okay. Therefore, pipeline laundry is potentially 4 times faster than non-pipeline. 20 loads would take about 5 times longer as one load, or 5 times as long as one load, while 20 loads of sequential laundry takes around 20 times as long as one load. So it's only 2.3 times faster in figure 4.23 because we only show 4 loads. So you really have to keep this going over and over and over in order to keep getting better and better and better and approaching that maximum. Okay. And so this goes back down to this basic idea that, at cycle 1, if we look back at cycle 1, they're exactly the same. So, there's no difference between, at least at cycle 1, between this non-pipelined and pipeline version. So it's not until this section where if we continued on and we constantly had groupings of 4, groupings of 4, groupings of 4, it's not until we hit that section that we're really utilizing the pipeline fully. So that's important to keep in mind. But generally when we're talking about a computer, we're not running a computer for 14 cycles, 15 cycles. We're running it for billions and billions and billions and billions of cycles. Okay. So the same principles apply to processors where we pipeline instructions execution. RISC-V instructions classically take 5 steps. So we can split it, just like we split the laundry into 4 sections, we can split the RISC-V instruction set into 5 sections. So this will be fetching from memory, or the instruction memory, reading and decoding the instructions, executing, accessing data memory if necessary, and then write back, or writing the result into a register. So we're going to be looking at a 5-staged pipeline example. Okay, and so here they give us some basic timings in picoseconds for the time it takes to do each instruction. So for something like a low double word that uses every single stage, it'll take about 800 picoseconds. But for something like a branch that will only do the instruction fetch, the register read, and the ALU operation, it'll actually only take around 500 picoseconds. So what do we have here? So we have a single cycle non-pipelined execution versus the pipelined execution. So here we have a fixed length of 800 picoseconds per instruction, no matter what type of instruction it is. And so these are consecutive load instructions. So here, what we can do is we can overlap them. So we just do the instruction fetch on the next clock cycle, while this instruction is reading the registers. The next instruction will be doing a fetch. In the next cycle, while this is calculating some address, the next instruction is getting the address out of the registers, and the next instruction is doing the fetch, and then they all end up finishing off eventually. And so we see we cut down significantly on the amount of time that we're saving. So in less than the time that it took to do 2 instructions here, we were able to fit 3 in, and potentially 4 in the time that it took for them to do only 2 instructions. So this is kind of the motivation for pipeline designs. Okay, some simple metrics that we can use for calculation. So how do we design instruction sets for pipelining? So we see that now we're having to split instructions now. So what considerations do we need to make for our instruction sets? Okay. So first, all RISC-V instructions are the same length. This restriction makes it easier to fetch instructions because we're all fetching and decoding the same length instructions. So something like x86, which I like to rag on x86, but it deserves it in some sense, where the instructions vary from 1 byte to 15 bytes, pipeline is considerably more challenging because you have variable length instructions. We were kind of talking about this earlier. It would be we can see that our regular and simple pipeline, breaks down immediately if we have to account for 1 byte to 15 bytes. So, but as we kind of talked about earlier, modern implementations of x86 translate x86 into simple operations that look like RISC-V instructions. Okay, so let's continue on. And let's look at pipeline hazards. So we saw that pipelining seems almost too good to be true, right? We just get this free 4x speed up with 4 stages of a pipeline. If we add like 5 stages, will we get, 5x speed up, 6 stages, 6x speed up? I mean, it seems that way, at least from the initial impression. But we see that it introduces something new, something that doesn't exist. It fundamentally doesn't exist in single cycle processors, which is pipeline hazards. So these are situations in pipelining where the next instruction cannot execute in the following cycle. I let that trail off there. It's just where the next instruction cannot execute on the following cycle, and that's usually because of some kind of dependency. And so we call these hazards, and we put them in 3 categories. So a structural hazard. So when a planned instruction cannot execute in the proper clock cycle because the hardware does not support the combination of instructions that are set to execute. So let's see where we can find one here. A structural hazard in the laundry room would occur if we use the washer-dryer combination instead of a separate washer and dryer. So if we had one machine that did 2 tasks, we can't use them both concurrently for different tasks. So as we said above, the RISC-V instruction set was designed to be pipelined, making it fairly easy for designers to avoid structural hazards when pipelining. Suppose, however, that we had a single memory instead of 2 memories. So instead of having a separate data memory and instruction memory, there was just one. If the pipeline in figure 4.25 had a 4th instruction, we would see that in the same clock cycle, the first instruction is accessing data from the memory, while the 4th instruction is fetching an instruction from that same memory. So let's go back to 4.25. Here we go. So let's get rid of some of this highlighting. So what they're trying to say here is that if we had a 4th instruction down here that was trying to fetch at this point, we see that data access would be trying to do it at the same time as fetch. So if we only had one memory structure, this would be a structural hazard. However, in the model that we're considering, that's not possible because we do have a separate instruction memory and data memory. So let's talk about data hazards. Let's talk about ones that may be more interesting. So data hazards, also called pipeline data hazard. When a planned instruction cannot execute in the proper clock cycle because data that are needed to execute the instruction are not yet available. So we're still crunching on numbers that we want to consume in the instructions that are right behind it. So let's take a simple example of an add and a subtract back to back. So if we add x19, if we add x0 and x1 stored in x19, we would have a stall because the next instruction in pipelining, the subtract, wants to consume this value x19 in the next clock cycle. So we can get past this with something like forwarding or bypassing, but it's probably useful for us to look at an example of why this actually is an error. So if we had fetch followed by a decode followed by execute followed by memory followed by write back, and then so this will be the add instruction. Let's zoom in a little bit. For the subtract instruction, I'm going to lose my ability to write here. It didn't like that. Oh, it only wants me to write at this granularity. Okay. So for the subtract, we'll have fetch, decode, no problems yet. Aha, execute. So at execute, we want this value of x19 and x3. However, x19 gets written back over here in this write back stage. So we need a way to get this value from here to here. And so there's a couple ways we can do that. One way, we don't stall. The other way, we just stall and we wait. So let's see what those are. So forwarding and bypassing. So forwarding, also called bypassing, is a method of resolving a data hazard by retrieving the missing data element from internal buffers rather than waiting for it to arrive in a programmer visible register. So we finished calculating x19 after execute. So we should be able to just forward this data immediately to the next stage, to this execute. And so that just is going to take a little bit of modification for our control in order to do that. So let's look at forwarding with two instructions. So for the two instructions above, show what pipeline stages would be connected by forwarding. So let's go ahead and look at the solution they give. Here we go. So here are our two pipeline stages. So basically what we're saying is that after we calculate x1 here, we already have the value, so we can just forward it to the next stage here so it can be the input to this subtract instruction. So this is forwarding or bypassing. It's a very powerful thing that we can do, but it doesn't fix every possible error, but it does fix some. Okay, forwarding looks very well and is described in detail in section 4.7. It cannot prevent all pipeline stalls, however. For example, suppose the first instruction was a load of x1 instead of an add. As we can imagine looking from 4.2.7, the desired data would only be available after the fourth stage of the first instruction in the dependence, which is too late for the input of the third stage. And so this is called a load use data hazard. This figure shows an important pipeline concept, 4.2.8, that is, we call a stall, and sometimes we call it a bubble. So what they're saying is, if we were to load something from memory, we would only be able to do it here. And so we're not able to go back in time and provide this value in the past. So we have to do something else, which is called a stall. And we'll show that here. And that's basically, we wait until this value is ready, and then finally we can forward it at memory. So these bubbles are just wasted cycles, just wasted cycle, wasted cycle. So here we only need to stall once in reality, because if we look at the original diagram, it's really just one clock cycle off. So these bubbles are added there for some reason, but we're really only stalling once, and that's right here. We see that our fetch continues as normal the next stage. Okay. So let's move on. Now we can look at something called control hazards. So the third type of hazard is called a control hazard, arising from the need to make a decision based on the results of one instruction while others are executing. So if we have something like a branch instruction come in, there's going to be instructions following the branch. However, should we start executing those before we know if we're branching or not? Or should we not? So that's typically what we call a control hazard. So going back to the laundry example, suppose our laundry crew was given the happy task of cleaning the uniforms of the football team. Given how filthy the laundry is, we need to determine whether the detergent and water temperature setting we select are strong enough to get the uniforms clean, but not so strong that the uniforms wear out sooner. In the laundry pipeline, we have to wait until the second stage to determine the dry, or to examine the dry uniform to see if we need to change the washer setup or not. So what do? So here's the first of two solutions. One of them is we just stall. One of them we just wait and we say, okay, I can't possibly know what this could be, so I'll just wait until I know for certain. It's conservative, but it works. However, it's slow. And we don't want slow computers, so we want something a little bit better. So the equivalent decision task in a computer is like we said, is a branch instruction. So let's see. So let's assume that we can put enough extra hardware so that we can test a register, calculate the branch address, and update the PC during the second stage of the pipeline rather than the third. Even with the hardware added, the pipeline involving conditional branches would look like 429. The instruction to be executed if the branch fails is stalled 1 extra 200 picoseconds clock cycle. So, pipeline showing stalling on every conditional branch as solution to control hazards. So here, we just stall. We just wait until the branch is resolved, and then we continue with whatever the next instruction is. So if it's the next instruction, so PC plus 4, we continue on. If we say branch and we have to go to a branch target, that's the one we go to. Okay. So the next thing we could do, and it turns out we can do a really good job at it, is something called branch prediction. So if you're sure you have the right formula to wash uniforms, then just predict it. You can, and it turns out nowadays with our branch predictors that we can get upwards of 90-95% accuracy at predicting branches. We're very good at it now. So most of the time we can say we're going to take this branch or we are not going to take this branch, and we know to a fairly good degree of certainty that that's the correct answer. And so this option does not slow down the pipeline when you are correct. So when you are correct, there's no penalty. If you're not correct, well, you need to make sure that the penalty's not terribly big when you miss. Derek, engineering today, do branch instructions usually predict false or predict true? Neither. They don't typically predict false or predict true. So they're adaptive. They're adaptive things that look at the past branch instruction to determine what they're going to predict next. They don't just say, oh, normally predict false or normally predict true. They use the past branch results to get that. So if you had, say, something with a bunch of loops, it's a bunch of for loops or something, or a bunch of while loops, then yeah, it would start predicting true every single time. But if you had something that was, I think normally most branch predictors start out with at least a baseline, predict that a branch is taken, just because with all like for loops or while loops, generally speaking, you'll always take at least one trip in a loop. But no, there isn't like some set thing of, I know there is like some data that the percentage of branches that are normally taken versus untaken, but the key point is branch predictors in computers, they don't make generalizations like that, they adapt to the program behavior, which is probably more of a longer answer than you probably wanted. So computers do indeed use prediction, and so if you ever wanted to know why things like Spectre and Meltdown are possible, it's because of this exact thing right here, branch prediction. So this is how I think Spectre is the one that this affects. I think Meltdown is out of order execution, but Spectre exploits branch prediction or speculative execution. Basically what I think Spectre does is it causes you to take a bunch of branches over and over and over, and so you start predicting branches, right? Because that's what a branch predictor is supposed to do. And so you predict a branch into an area you're not supposed to go into, and then you raise an exception. And then you crash the program at that point, but the prediction's in this like quasi state, I think they call it. And then because it's in that quasi state, it actually doesn't recover, and it doesn't say, oh, you can't do this anymore. So you're left with like these remnant values that you can access. I think that's how Spectre works. I forgot how Meltdown works. It's a similar thing though. Okay, so let's see what happens here. So one simple approach is to predict all ways that the conditional branches will be untaken. When you're right, the pipeline proceeds at full speed. And only when conditional branches are taken does the pipeline stall. So if we always don't take the branch, then we just continue on as normal. However, if we do take the branch, well, we have to do some correction. We have to stall a bit, and then we have to fetch the next instruction correctly. So whatever we were executing here, we have to drain the pipeline of. We have to ignore those values. So a more sophisticated version of branch prediction, so now we're getting fancy, would have some conditional branches predicted as taken and some as untaken. So in our analogy, the dark or home uniforms might take one formula, while the light or road uniforms might take another. In the case of programming, at the bottom of loops are conditional branches that branch back to the top of loop. Since they are likely to be taken as they branch backwards, we could always predict taken for conditional branches if they branch to an earlier address. So this kind of goes into your point more, Derek, that there are certain patterns that we can look at. And so one of these things is whether or not we're branching to a previous address or to a later address. So if it's to a previous address, we can say it's probably part of a loop. We'll always predict it true. And if we do a for loop 1,000 times, we'll be right. 900. We'll be right for 1,000 times, and then the last time we'll be wrong, and then we'll have to do some minor correction. But if we're only wrong 1 out of 1,000 times, hey, I mean, I think that's pretty good. So such rigid approaches to branch prediction rely on stereotypical behavior, and they don't account for the individuality of a specific branch instruction. So typically we use something a little more sophisticated, so dynamic hardware predictors in stark contrast make their guesses depending on the behavior of each conditional branch. And they may change predictions for a conditional branch over the lifetime of the program. So following our analogy, in dynamic prediction, a person would look how dirty the uniform was and guess at the formula, adjusting the next prediction depending on the success of the recent guess. So this basically says we can use our previous history and our current knowledge to make a better prediction than only having a set guess. So one popular approach to dynamic prediction of conditional branches is to keep a history for each conditional branch taken, or for each taken and untaken, and then use this recent past behavior to predict the future. And so this has been used to, as I said, great success, like over 90% prediction correct. When the guess is wrong, the pipeline control must ensure that instructions following the wrongly guessed conditional branch have no effect and must restart the pipeline from the proper branch address. So generally call this draining the pipeline or squashing instructions. Okay. So there is a third approach, apparently, called delayed decision. So in our analogy, whenever you're going to make such a decision about laundry, just place the load of non-football clothes in the washer while waiting for football uniforms to dry. As long as you have enough dirty clothes that are not affected by the test, this solution works fine. So called a delayed branch in computers, this solution actually used by the MIPS architecture. So this is the idea of if we can find other work to do while we're still trying to figure out what we're supposed to do, then oftentimes this can be a good alternative. But most of the time, we do this dynamic branch prediction. So let's do a little pipeline overview summary. So like we're saying, we're trying to exploit parallelism. But specifically, we need to be specific when we're talking about the type of parallelism. We're trying to exploit instruction-level parallelism. These are instructions that we can overlap with each other and not cause a ton of errors. And we'll see how we can even limit the number of errors associated with ILP later on. That might not even be until we do the full computer architecture, a quantitative approach course. That's when you start to learn about the real architecture. That's when you start to learn about how computers really work. That's the fun stuff. We also looked at some pipelining problems. So these are going to be those hazards we saw. Okay. So what's the big picture? It's important that we always understand the big picture, isn't it? Pipelining increases the number of simultaneously executing instructions, so our instruction level parallelism, and the rate at which instructions are started and completed. Pipelining does not reduce the time it takes to complete an individual instruction. We're just improving our throughput. So we need to keep in mind whether we're optimizing for throughput or we're optimizing for latency. So just because CPUs are generally considered to be latency optimized processors, it doesn't mean that they don't have throughput optimizations in them as well. They just don't have as many throughput optimizations as something like a GPU. So there's our early introduction to pipelining, and as well as things like branch prediction. So let's move on into pipelined data path and control. So we talked about some high-level ideas of how pipelining works. So how would this work in reality with the data path, with the control that we were talking about? So like we said earlier, we're going to split the pipeline into 5 stages. A stage for fetching instructions, a stage for decoding instructions, for executing, for memory operations, and for write-back operations. So write-back means writing back to the register file. Memory means we're accessing data memory, not instruction memory. Execution is when we're using the ALU. Decode is when we're reading the register file, and then instruction fetch is when we're reading instruction memory and getting our instructions. Okay, so here we have kind of a high-level view. So we can really start splitting the different stages, the different pipeline stages, into different parts. So at this first stage, we're fetching an instruction, meaning we have to go to instruction memory. At decode, that's when we're splitting this instruction into its individual parts, its different sets of bits to access registers, maybe to go to this immediate generation, and then to read them out on the other side. Then in execute, that's when these register values and immediate values go to whatever they need to go to. So if it's an R-type instruction, these registers go to the ALU. If it's a branch instruction, this immediate value has to be routed up here, and it'll make this calculation. And then it'll be put on the other side of the ALU. Once we get to the memory access stage, whatever address we calculated here, we'll go to data memory, and we'll decide here whether or not we're doing any data reads or data writes. And then finally, at write back, if we're doing something like a load instruction, we're going to have to read out this data from memory and take it all the way back to the register file. So write it back to the register file. So that's the basic idea of splitting this pipeline that we already had, or splitting this single cycle processor we already had into these 5 stages. That's typical for something like RISC-V or the MIPS instruction set architecture. Okay, let's see. So here we have another split to kind of understand more about what this means as far as doing some instructions. So here we have, of course, instruction memory where we're fetching. Then in the next cycle, we'll be reading from the register file while the next instruction begins fetch. So for this load, we're going to calculate an address. Here we're going to read out the address, and we'll fetch another instruction. And here, we're loading something out. So we're actually not going to be, we're going to be loading something from data memory from the register, and then finally we want to write it back here. So load, we get something from data memory, it goes out to the next stage to the register, and so on and so on and so on. And so this is assuming pipeline execution. So basically we can just overlap instructions. And there's no dependencies here because we're just accessing data memory, but we'll never be accessing data memory in the same clock cycle of another instruction. So we're not going to run into any hazards. So we're okay here. Okay, let's see. So what does figure 4.32 suggest? It seems to suggest that 3 instructions need 3 data paths. Instead, we add registers to hold data so that portions from a single data path can be shared during instruction execution. For example, 4.32 shows the instruction memory is used during only one of the 5 stages of the instruction, allowing it to be shared by the following instructions. So what they're saying is that after, say, let me get rid of some of these. So in instruction 1, in the first cycle, we're using the instruction memory. However, once we get to cycle 2 and we move on to decode, we're no longer using the instruction memory. So the next load instruction can use instruction memory. And then this goes on and on and on. So while we're doing some calculation of address, this guy can give up the instruction memory. He can take the register file, and then the next instruction can use the instruction memory. So it's this constant trade-off of who's using which functional unit. But we don't need to replicate each of these, say, 3 times or X amount of instructions that we're using. And so this is typically how we represent this in a figure. So we generally have these big blocks in between these stages that we route some control logic through. And so we'll use these big dividers between instruction fetch and decode, instruction decode and execute, execute and mem, and then mem and write back. And so these will be the things that we'll use to maybe forward a value or bypass a value or inject stalls. This may not forward these values if we know that there's a stall. And that will be given by some, up here, there'll be some control logic that will control each of these little buffers right here. Okay. Let's see. So what do we have here? So what is 4.34 telling us? So figure 4.34, instruction fetch and instruction decode. First and second pipe stages of an instruction with an active portions of the data path highlighted. The highlighting convention is the same that's used in 2.6 as in 4.2. There is no confusion when reading and writing registers because the contents change only on the clock edge. Although the load needs only the top register, in stage 2, it does not hurt to do potentially extra work. So its sign extends the constant and reads both registers into the instruction decode execute pipeline register. We don't need all 3 operands, but it simplifies control to keep all 3. Okay. So this is pretty simple. This is just saying that the active portion at each, or what the active portion is in each clock cycle. So in something like instruction fetch, we're only really caring about what's coming out of instruction memory and going into this pipeline register. Once we're in decode, what we care about is what came out of instruction memory that we split off, and then what is being read. So what is being put through the registers into this the instruction decode execute pipeline register. And then let's see, the same thing happens with execute. So the third stage of the load instruction, highlighting the portions of the data path used in the pipe stage. So we're going to be using from here the address that we get out. We're going to be selecting which value we're using, which for the load instruction will be what came from the pipeline, which will be right here. That was originally this sign extension. And then this will go to the ALU, and which of course we want to save now in the execute mem pipeline register. Then finally, we're going to get to memory. Remember, this is a load instruction. So what do we care about? We care about what's coming from execute mem, so this address that we're getting, and we care about the data we're getting out of the data memory. So this is a load instruction, so what are we loading? And then finally, in write back, what do we care about? We care about what's being read from the mem write back pipeline register. We care about this multiplexer. We want to make sure that we're reading the value from memory, so we want this value to be 1, because if it was 0, we'd be coming from the execute mem pipeline register for this ALU. And then we care about the front end of the register file. So what we mean by only highlighting half of the register file in this section is that we could potentially be writing something to the register file at the same time that we're reading to other values. These can be split up. So we only care about, in write back, we only care about the front half of the register file and what value we're writing in. Okay. So they go through some more examples, but we can skip most of these. We get the idea. So here we see some correction. So the corrected pipeline data path to handle the load instruction properly. So the write register number now comes from the mem write back pipeline register along with the data. The register number is passed from the ID pipe stage until it reaches mem write back. So let's see what they did here. So what they did was they saved this original value from decode for the write register. They passed it along until they were ready to use it at the write back stage, at which point they took the data from here and they took which register and they put them both back. So that's a small correction that we have to make in order to support something like that. Okay. So we can graphically represent pipelines like this, where we can highlight the shades of the functional units that we're using at each clock cycle. So here we have, we're only using the instruction fetch stage. We're only using the front half because we could potentially be writing the new program counter value at the same moment in instruction memory. For the register file, when we're accessing these registers, we're only using the front half because we could be writing to the register file from some later stage. The ALU, we have complete control. When we're looking at data memory, we might be writing to data memory at the same time we're reading from it, so we only want to care about the front half. And then at write back, we only care about the front half of the register file because we could be writing to it in write back, hence why it's called write back. And so typically, when we're doing these things, we'll just abbreviate this as fetch, decode, execute, mem, write back. Okay. Let's see. Now let's get into pipeline control a little bit more. So let's see what this quote is. In the 6600 computer, perhaps even more than any previous computer, the control system is the difference. So apparently in the 6600, that's when they really introduced the idea of a control structure. I'm not sure what they did previous to this. So just as we added control to the single cycle data path, we now add control to the pipeline data path. So how do they add control? So now the control seems to be pretty similar. We still need an ALU control that controls what operation we're doing. However, now instead of directly feeding ALU control, we have to forward it through these pipeline registers. Same thing with branch instructions. If we get a 0 result for a branch of equals, we have to forward it through pipeline registers to this comparison and eventually write it back. So it's pretty similar. There's a lot of parallels, but a couple differences. Namely, we have to be utilizing these pipeline registers. Let's see. Is there anything interesting else? So we see some more truth tables where we can work out the logic to figure out exactly what kind of gates we're going to need, but that's more of a trivial exercise reserved for a logic design class. So here we see that for the control, for the first stage, we need to pass forward everything we need for the execute stage, the memory stage, and the write back stage. But once we get to the execute and memory stages, we've already passed execute, so we don't need to forward any logic from execute anymore. So we really just need the logic for the execute stage or for the write back stage and the memory stage. Now, once we're here, we're already in the memory access stage. So the only thing we need to forward past this point is the write back information. So we have this kind of waterfall cascading amount of data lines that we need to forward. ADB7 just subscribed with Twitch Prime. Hey, thanks a lot, man. I really appreciate it. If you like the content, I'll be posting it all on YouTube, and you can look forward to some shorter form 10 to 15 minute lecture videos coming soon. Okay, so let's move forward. So here we have with that cascading kind of waterfall structure built into the pipeline now. Oops, here we go. So very similar. We have our control up here, and we build in a couple extra lines to forward this control logic. So not only do we have these pipeline registers for storing values, but we also have pipeline control structures in here as well. All right, so let's talk about data hazards, forwarding versus stalling. So we talked about these at a high level, but we haven't talked about if we were to implement them in our actual pipeline architecture, what would that look like? So we have a nice Douglas Adams Hitchhiker's Guide to the Galaxy quote. What do you mean? Why, it's got to be built. It's a bypass. You've got to build bypasses. So let's see. So here we have that similar type of those similar types of hazards. So we have a subtraction instruction, but we're immediately trying to consume the result in the next clock cycle. And then likewise in the next clock cycle, we're trying to consume x2 again. So then here we're consuming them again and again. So all of these are consuming this x2 value that is produced initially. So, we can already kind of see, well, by the time we hit that store instruction, well, x2 is probably going to be generated. But what about for the AND? What about for the OR instruction? Maybe not. So how would this sequence perform with our pipeline? So let's look at figure 4.50 to see how it would. So what needs to happen? So we have 4 dependencies from this specific pipeline, or from this specific value. So all the dependent actions are shown in color, and the CC1 at the top figure means clock cycle 1. So this just says clock cycle 1. So the first instruction writes into X2, and all the following instructions read X2. This register is written in clock cycle 5, so we're not writing to the write back until here, clock cycle 5. So the proper value is unavailable before clock cycle 5. So this is the first point at which we can start forwarding or bypassing instructions. Okay, and so here we see basically what happens here. So for this AND instruction, we can bypass it so that when we're doing this register reads, so when we're trying to get X2, instead of getting it from the register file, we're getting it from this write back stage. And then the same thing here. So here, instead, let's see. So it looks like we're just forwarding it to each of the register files at each of these stages. However, we'll see with these two, it makes a little bit less sense. And even for this one, it doesn't make sense because it looks like we're bypassing into the future. So it looks like we're taking something from the register file into the future. But in this case, this value is already in the register file, so in all honesty, it will just look like this. Or let me get the pencil out. So if it's already in the register file by here, then we don't need to forward it. It's already here. Same thing here. So here we might even bypass it to just the ALU. But the pipeline might not be built for that, so let's see if they talk about it. Let's go back to yellow. So the last potential hazard can be resolved by the design of the register file hardware. What happens when a register file is read and written in the same clock cycle? We assume that the write is in the first half of the clock cycle and the read is in the second half, so we can do both writes and reads at the same time, or in the same clock cycle at least. And so this is the case for many implementations of register files. So figure 4.50 shows that the value is read for register X2, so that's our value in question here, X2, would not be the result of the sub-instruction unless read during clock cycle 5 or later. So for everything in this cycle or later, so for here and for here, because this is clock cycle 5 or later, we're doing okay because it's already in the register file. However, our problems still lie with these first two instructions. Let's see. As mentioned in 4.5 earlier, the desired result is available at the end of the execute stage of the sub-instruction, or clock cycle 3. When are the data actually needed by the AND and the OR instructions? So which are the AND and OR? So those are the following two that we need to forward or bypass to. The answer is at the beginning of execute. Okay, so cycles 4 and 5 respectively. Thus, we can execute this segment without stalls if we simply forward the data as soon as it's available to any units. So how does forwarding work? For simplicity, in the rest of the section, we consider only the challenge of forwarding to an operation in the execute stage, which may be either an ALU operation or an effective address operation or calculation. So for memory, we calculate addresses, so this is called an effective address calculation. Okay, so this means that when an instruction tries to use a register in the execute stage, then earlier instruction intends to write to the write-back stage, we actually need the values as inputs to the ALU. So we need our write-back as inputs to the ALU now, as well as to the register file. So a notation that names the fields of the pipeline registers allows for more precise notation of dependencies. For example, at the decode execute, register RS1 refers to one register whose value may be found at the pipeline register, instruction decode execute. Okay. So using this notation, the two pairs of hazard conditions are execute memory, register read must equal decode execute register RS1. So let's see if we can make sense of this. So from execute mem, that's where we have, okay, so these two are going to be the forwarding of this first instruction here, this sub, because it's going to be in this execute mem, and it's going to be the same register. And we're going to forward it to the execute stage for both of these instructions. Now for mem write back, this is actually pretty interesting. Using this notation, the two pairs of hazard conditions are so let's see if we can find them here. So this is fetch, decode, execute, memory, write back. So the first one that they talk about is execute in mem. So that's right here. Here. That's execute in memory. And then the other one is decode and execute. So decode and execute is here. Okay. So let's continue on. That makes more sense now. The first hazard in the sequence on page 295 is on the register X2 and the result of this subtraction and the first read operand of AND X12, X2, X5. This hazard can be detected when the AND instruction is in the execute stage and the prior instruction is in the mem stage, so that the hazard 1A execute mem register read or register RD is equal to the execute stage X2. So this is saying that at the execute stage we can forward some value. So let's see, this is sub and yeah, that's these right here. So it's just saying that we can forward back this value of X2 into this other stage while it's in execute. Okay. So here we have the same kind of thing where we have this read after write kind of dependency. And we see that we have that again here, but it's less of a problem because it's a little bit further away. And by the time here, we actually don't have a problem at all because the sub instruction should be finished by then and should already be at the register file. And that's what it says here. So this sub OR is a type 2B hazard. So this means that the mem write back must be set equal to this decode execute register, which is X2. So we need to forward this value of X2 that we get from the subtraction. The two dependencies on sub-add are not hazards because the register file supplies the proper data for the next one. So this OR instruction actually executes properly. And so does the add, and so does this store data. Okay. So this is kind of that data forwarding in action. So in some cases, we need to forward it immediately. So in the case of this AND instruction where we need it immediately at execute, we have to forward it from this. So this will be the execute mem pipeline register. For something like the next one, we can forward it directly from the mem write back register. And then for something like this add, we don't need to do any forwarding at all because it's already in the register file. And then the same thing for the store data or store instruction. Okay. A little bit complicated, but we got there. Let's see. So we also need to add something called a forwarding unit. So if we're going to be passing values to different parts, we need to remember that our actual hardware isn't structured in this tier manner. If it was structured in this tier manner, that means we would need to, say, have 6 times or 5 times the amount of hardware. So we really just have the same overall kind of pipeline. So how do we do this kind of forwarding? Well, simple. We take these register values, we give them to another kind of control unit, which we will call a forwarding unit, and it will now decide, we'll add another input to these multiplexers, and instead of only deciding whether it's coming from maybe a register value or maybe it's coming from a assign extended immediate value, well, maybe it's coming from a forwarding unit now. So we complicate our control logic a little bit, but we do so with the ability to no longer have a lot of these hazards, which is really important for us. Okay, let's move on. Okay, we have some more examples here. So here's our more fleshed out pipelined RISC-V processor, where we have our control unit. We have our forwarded control that we need for each of the stages. Then we have our data forwarding unit, where we can take our values after the execute stage or from the write back stage and forward them to wherever they need to go. So typically we're forwarding values to be executed on, so whether or not we need them as this register input or this register input, we can forward them to either of those multiplexers. So let's talk a little bit more about this, just so we clear up any confusion. So forwarding can also help with hazards when store instructions are dependent on other instructions. Since they use just one data value during the mem stage, forwarding is easy. However, consider loads immediately following stores. Useful when performing memory-to-memory copies in the RISC-V architecture. Since copies are frequent, we need to add more forwarding hardware to make them run faster. If we were to redraw this previous figure that we just saw, replacing sub and with load store, we would see that it is possible to avoid a stall since the data exists in mem write back register of a load instruction in time for use in the mem stage of a store instruction. We would need to add forwarding into the memory access stage for this option. So they do my favorite thing that is oftentimes left in research papers where they don't want to have to write this all out, so they say we leave this modification as an exercise to the reader. Aren't they just grand? Okay. So, yep, they added this forwarding unit. They're just explaining this a little bit more. Okay. Is my highlighter going to work? Yeah. Is it going to work zoomed in? Nope. Okay. So apparently my highlighting only wants to work at this highlighting level. That's okay. So we already talked about data hazards and stalls. So we can skip most of this. So let's go ahead and kind of wrap this up and talk about the big picture before we talk about a couple other concepts. So what's the big picture here? So although the compiler generally relies upon the hardware to resolve hazards and thereby ensure correct execution, the compiler must understand the pipeline to achieve the best performance. Otherwise, unexpected stalls will reduce the performance of compiled code. And in reality, people that develop compilers don't explicitly know everything about the pipeline. A lot of times that's obfuscated away from us. So we have to make some good guesses, and we can do a fairly good job. But at the end of the day, nobody's perfect. So regarding a remark earlier about setting control lines to 0 to avoid writing registers in memory, only the signals reg-write and mem-write need to be 0, while the other control signals can be don't care. So this is just some clarification on how we design this control logic. Okay. So we've talked about these data forwarding hazards, but we still haven't talked about control hazards. So what happens if we say mispredict a branch, or in the case of stalling and not doing any branch prediction, what happens then? So let's get into it here. So that's what we're talking about. So the impact of the pipeline on branch prediction. So if, say, we want to branch to this instruction, say we want to branch all the way down here. So if we continue our normal pipeline execution, we'll start 3 instructions before we know about branching. So what do? We're already modifying some state within the processor, so we have to have some way of recovery to make sure we don't make any lasting or permanent changes. Okay, so this section on control hazards is shorter than the previous sections on data hazards. The reasons are that control hazards are relatively simple to understand, they occur less frequently than other hazards, and there is nothing as effective against control hazards as forwarding as against data hazards. So we had some really good ideas like forwarding that work for some hazards, but for branch hazards, not the case. We can't get by that easily. We'll see that once we do a more advanced computer architecture book that it can get very complicated. So we look at 2 schemes for resolving control. We're going to assume the branch not taken scheme. So one improvement over branch stalling is to predict a conditional branch will not be taken and thus continue execution down the sequential instruction stream. So we'll assume some naive instructions. So what do we need to do? In case we predict incorrectly, we have to take the instructions we've executed so far and we need to flush them. And so what do we mean by flush? It means we need to discard instructions in the pipeline, usually due to an unexpected event. So in this case, we need to be able to flush instruction fetch, instruction decode, and execute, because we know that after the 3rd clock cycle, after a branch instruction, the branch will have resolved and we will have known if it's a branch taken or a branch not taken. So reducing the delay of branches. So one way to improve conditional branch performance is to reduce the cost of a taken branch. So far we've just assumed that the next BC for the branch, for a branch is selected in the mem stage. But if we move the conditional branch execution earlier in the pipeline, then fewer instructions need to be flushed. So instead of having our original design where we figure out about our branch target here, well, what happens if we move our branch resolution earlier? That means there's going to be less overlap of instructions that need to be flushed, as they just said. So let's see what we have here. So here we see we have this new hazard detection unit that we're going to be putting in. And let's see. So in the decode stage of clock cycle 3, determines that a branch must be taken, so it selects 72. So let's see if they go through the entire thing. So we're going through this example right here. So show what happens when a branch is taken in this instruction sequence, assuming the pipeline optimized for branches that are not taken. So this means that we'll be executing sequentially. So this means that even before this branch is resolved, we'll already start executing this AND instruction. So what's the answer? So we'll see figure 4.60 shows what happens when a conditional branch is taken. So unlike 4.59, there is only one pipeline bubble on a branch, on a taken branch. So what was the previous one? 4.59. So on 4.59, we had multiple bubbles because we figured out much later on that a branch was taken. Versus here, after we've moved the pipeline around a bit and we shifted it around, we've moved it down to only a single bubble. So let's see if we can get to that bubble picture. They don't have it. Okay. So here we only have a single bubble. We're now in this decode stage. We're not doing anything. We have to flush this section in clock cycle 3. And then in clock cycle 4, we start filling it with the correct instruction. So let's talk about dynamic branch prediction. So we've talked about very basic branch prediction, but we haven't talked about dynamic yet. So with dynamic branch prediction, we usually use something called a branch history table, or a small piece of memory where we keep track of the previous branch's results, so whether branches have been taken or not taken. Those are the informations that we're going to be using to make our decisions. And so one of the really common schemes of using is, or not a really common one, but a very simple one to understand, is a 2-bit prediction scheme. So in a 2-bit prediction scheme, we don't immediately switch from, say, taken to not taken or taken to not taken for a prediction. It has a little bit of hysteresis or hysteresis. I'm never sure how to pronounce that. So basically what happens is, say if we start at a predict taken state. If we get a not taken branch, we move to a weak predict state. And then finally, if we're not taken again, we move to a not taken state. And then if we're not taken again, we finally move to this hard not taken state. And so we have a little bit of saturation here. So if we're not taken, and then we get a single branch that's taken, we're still going to predict not taken, but if any more comes in, we'll start predicting taken. So this is a very simple setup we can use. It's a 2-bit prediction scheme. Very little hardware. Very little. So some elaboration. A branch predictor tells us whether a conditional branch is taken, but still requires the calculation of the branch target. In the 5-stage pipeline, this calculation takes 1 cycle, meaning the taken branch will have a 1-cycle penalty. One approach is to use a cache to hold the destination program counter or destination instruction using a branch target buffer. So a branch target buffer being a structure that caches the destination program counter. So this says that, okay, well, if we are able to predict what branch, if we're able to predict a branch's outcome, so taken, not taken, we should also be able to predict the location of that branch. And then we have things like correlating predictors, which a branch predictor that combines local behavior of a particular branch and global information about behavior of some recent number of execution branches. So here we're kind of getting information from a ton of different areas in order to make a really good kind of predictor. So we're not just looking at our own local branches, but we're looking at a more global level of total branches. Then we have things like a tournament branch predictor as well. So a tournament branch predictor with multiple predictions for each branch and a selection mechanism that chooses which predictor to enable for a given branch. So now we're not locking ourselves into a single line of prediction. We can have multiple lines that we can use some kind of control to select on. Okay, so what else do we have in this chapter? So we should also know a little bit about exceptions. Well, we're finishing up today. We have about 10-12 minutes left in the stream. So we'll finish it up talking about some exceptions. So what are exceptions? So control is the most challenging aspect of processor design. It is both the hardest part to get right and the toughest part to make fast. One of the demanding tasks of control is implementing exceptions and interrupts. Events other than branches that change the normal flow of instruction execution. So that's what an instruction, or that's what an exception or interrupt is. They were initially created to handle unexpected events from within the processor, like an unidentified instruction. So if something happened to an instruction while it was being decoded, or maybe a bit flipped here or there and it didn't understand it, it would cause an exception. So the same basic mechanism was extended for I/O devices to communicate with the processor. So if we need a way to interrupt the processor, we can cause an exception, a forced exception. So an exception, also called an interrupt, is an unscheduled event that disrupts a program execution used to detect undefined situations, and then an interrupt, an exception that comes from outside the processor. So some architectures use the term interrupt for all exceptions. So another little bit of naming consistency issues here, which can be a little bit confusing. So let's talk about in terms of from where and then the RISC-V terminology. So if we get a system reset, it's external and we call it an exception. However, for something that's I/O that's external, we call that an interrupt. So if we invoke an operating system from user program, it's an internal and it's an exception. An undefined instruction is internal and an exception. And the hardware malfunctions, if something goes wrong with a processor, it can be either external or internal, and then it can either be an exception or an interrupt. Okay, so how are they handled in RISC-V? So the only types of exceptions that our current implementation can generate are execution of an undefined instruction or a hardware malfunction. So we'll assume a hardware malfunction occurs during an instruction, add X11 with X12 and X11. As the example exception in the next few pages, the basic action of the processor must perform when an exception occurs is to save the address of the unfortunate instruction in the supervisor exception cause register. So basically we want to just save, okay, where did we fail, so that we know specifically. So it'll save the PC value of this instruction. And the operating system can take the appropriate action, which may involve providing some service to the user program or some predefined action. Okay. So then there are things called vectored interrupts. So an interrupt for which the address to which control is transferred is determined by the cause of the exception. So this is generally when we have an entire table of different predefined code that we can execute, or pointers to predefined routines that we can kind of pick from. And so depending on what happens, we basically choose the corresponding pointer and we go to that predefined routine. Let's see. So they add some extra hardware in order to handle some of these exceptions. So we already handled hazard execution, but we're also handling flushing instructions now. And then the only other thing we have to do is saving the program counter value to return into that specific register, the supervisor exception program counter. Okay. Let's see. So we've talked a lot about parallelism, and so we've talked a lot about instruction level parallelism and the fact that being able to pipeline instructions is already indicative of instruction level parallelism, because it means that we can do instructions in parallel or parts of instructions in parallel. So that's what we mean by ILP. So then there's also things called multiple issue, where instead of just issuing a single instruction per clock cycle, well, maybe we can launch multiple instructions per clock cycle. Static multiple issue. It's an approach to implementing a multi-issue processor where many decisions are made by the compiler before execution. So static means it's not happening at runtime, it's happening ahead of time. That's not exactly what static means, but so static in this case means it's predetermined. And then there's dynamic, which is an approach of implementing multiple issue processor where they're determined during execution by the processor. And then there's some higher up concepts such as prediction and speculation, where we can predict, say, Lev, what's wrong? Lev, are you having an issue? Is the stream not working for you? It's working fine for me. Okay. And so we have prediction and speculation, so we can predictively start executing instructions. So we can take instructions and start executing them maybe out of order or ahead of time in making our best guesses. And we have to introduce some logic later on to fix these if we do something wrong, but the concept is very fundamental to how we get so much performance nowadays. Unfortunately, it's also the reason why we have attacks like I mentioned earlier, Spectre and Meltdown. Those are both based on prediction and speculation. Okay. Okay. So we already talked about static. And then there's a very long instruction word, or VLIW, which is a style of instruction set architecture that launches many operations that are defined to be independent in a single wide instruction. So if, say, we wanted to do 10 adds, a VLIW instruction would be able to, say, add 10 things together with a single instruction. Okay. So let's see. I think that's most of the key points that we wanted to see. For the rest, I'll have to do some videos on because we're running out of time today. So I'd like to, before we close out the stream, go over at least the pitfalls and fallacies section. The pitfalls and fallacies section is always a fun time. So make sure to check out the YouTube channel if you want any additional content. Okay. Well, it looks like the stream went down. My apologies. Let's see if I can at least do this so that I can export it to YouTube. Let's get to those pitfalls and fallacies. My goodness, there's a lot of figures in this chapter. Lots of illustrations. Good for presentations. Pitfalls and fallacies. So, of course, a fallacy that we always have is that pipelining is easy. As we've seen with so many, as we've seen as an issue with so many of the hazards we've had to deal with, pipelining can be very hard. So another fallacy is that pipelining ideas can be implemented independent of technology. But we've seen that with all the hardware that we need to add to actually implement these pipeline things, we need the transistors. So it's really only made possible by technology scaling. So another pitfall is the failure to consider instruction set design can adversely impact pipelining. So if we have something like a variable size instruction set, we see that it's going to be very hard for us to consistently store types of data because they're going to be different sizes. So how do we design for that? So that's a pitfall that we can fall into. And so that looks like about all we have for today. Listen, I'm sorry if the stream cut out for you. If it didn't, I appreciate you for being here. ADB7, thank you for the Twitch Prime. I appreciate it. You'll always be in my heart as my first Twitch Prime sub. Listen, everyone, I'm Nick from Engineering Today, and you've watched Page by Page. And today we went over Chapter 4 of Computer Organization and Design, the RISC-V edition. Thanks for joining me.